Hello friends, welcome to Learners Forum. So from this video, let us see the previous year question papers of TNEB AE exam for 2018. So under part 3, let us solve the technical questions now. First question, if all the three resistances of a given delta network are 15 ohms each, then three resistances of equivalent star will be. So to solve this question, we need to know the conversion from delta to star. So to convert a delta network into a star network, the formula used is RA, which is equal to, we have to represent in terms of A, so it is RAB into RAC divided by the total resistances. So RAB plus RBC plus RCA. Next for RB, we have to write in terms of RB now. So in the numerator, we will get in terms of RB resistance, which is RBC into RAB divided by again the total resistances. So RAB plus RBC plus RCA. Next for third resistance RC in terms of RC now. So in numerator it will be RAC into RBC divided by RAB plus RBC plus RCA. So this is the formula for delta to star conversion. Let us substitute the values. Given is the delta network with 15 ohms each, which means the values of the three resistances, which is RAB is equal to RBC, which is equal to RCA, which is equal to 15 ohms. So substituting this value in RA, RB, RC, we will get RA is equal to RAB is 15 into RAC 15 divided by 15 plus 15 plus 15, which is equal to 15 into 15 divided by 45. So cancelling this, we will get 3 and here it will be 5, which is equal to 5 ohms. Similarly, we will get the same value for RB and RC because all the values are 15 ohms each. So the value of RA, RB, RC are 5 ohms for the equivalent star, which is available under option 4, which is our correct answer. Next question. The phenomenon known as early effect in bipolar transistor refers to reduction of effective base width caused by. So to solve this question, we need to know what is an early effect first. So let us analyze the concept of early effect. So early effect is caused by applying large values of collector base reverse bias. Increasing the value of collector base reverse bias will lead to early effect. So under the depletion region, the base value will be reduced and the base width also will be reduced, causing base concentration to get increased. So whenever the base width is getting reduced, it will lead to less recombination of electrons of carriers. So the collector current will get increased, which causes early effect. So this is the concept of early effect. So the question is all about the reduction of effective base width is caused by. So here the base width is because of the values of collector base reverse bias, which is getting large. So under the given option, reverse biasing of base collector junction, which is available under option 2, is our correct answer. Next question, in a JFET, drain current is maximum when VGS is. So to solve this question, we need to know the formula for drain current, which is given by ID, which is equal to IDSS into 1 minus VGS divided by VP, the whole square. So under this equation, VGS refers to gate source voltage. Whenever it is given as 0, substituting this, we will get it as 1 minus 0, which is equal to just the value of IDSS, which is the maximum value of current possible. Next, when the value of VGS is equal to VP, then substituting that over here, we will get it as VP by VP, which get cancelled, which is 1. 1 minus 1 will be 0. So the drain current ID will be equal to 0, which is the minimum value. The question is all about the maximum value when the value of gate source voltage is. So to get the maximum value, we have to set the VGS as 0 to get the maximum current, which means option 1, 0 is our correct answer. Next question, what is the minimum number of 2-input NAND gates used to perform the function of 2-input OR gate? So we have to perform an OR gate function using the NAND gate. That is the question about, and how many number of NAND gates are required is the question. So y is equal to a plus b refers to the OR gate function. We can write the same function as a plus b the whole bar, which means it is also equal to a plus b. Now using the De Morgan's theorem, we can write the equation as a plus b the whole bar is equal to a bar dot b bar. So a bar dot b bar the whole bar. Now we can implement this equation using NAND gate. So first we take a NAND gate and combine both the inputs to the single input A. Similarly, the other NAND gate combining the two inputs with the input B. So the output of this gate will be A dot A followed by bubble. So it will be A dot A the whole bar. So A bar. And here it will be B bar. So now let us combine these two inputs to one more NAND gate, and we can get the output as A bar dot B bar the whole bar, because it is a NAND gate. So we have got the similar equation like the previous one, which refers to OR gate function. So comparing this, we will get the number of NAND gates, which is 1, 2 and 3. So to represent a 2 input OR gate, we require 3 NAND gates. So option 3 is our correct answer. Next question. A bit R to R DAC converter has a reference of 3 volt for a digital input code of 0110. What would be the equivalent analog output in volts? So to solve this question, let us write it for n bit type under digital to analog converter. So the output voltage is given by V0, which is equal to minus V divided by R into a n minus 1 by 2 power 1 plus a n minus 2 by 2 power 2 plus till a naught divided by 2 power n. So given is the bits as 0110. So these are the bit values, and it is also given as 3 volt as the reference voltage. So before substituting the value, we need to know that we have a reference, we have a feedback resistance with a value of R ohms. So substituting the value over here, we will get it as minus 3R divided by R, which is a feedback resistance, into a n minus 1, which means the first bit. So it is substituting the value of 4, we will get it as A3, A2, A1 and A0. So the A3 value is 0 by 2 power 1, 1 by 2 power 2 plus 1 divided by 2 power 3 plus 0 divided by 2 power 4. So for n is equal to 4, we have got the 4 bits. Cancelling R, we will get the remaining as minus 3 into the first and last term will get cancelled because it is 0. The remaining is 1 by 4 plus 1 by 8. Simplifying this, we will get minus 3 into 3 by 8. So it is equal to minus 1.125 volt. So this answer is belonging to option 4, which is our correct answer. Next question. The concentration of minority charge carriers in an extrinsic semiconductor under equilibrium is. So this question was asked in ESE exam 2014 question paper. Now let us solve this question using the concept of concentration of charge carriers in extrinsic semiconductor type. Starting with law of mass, Np is equal to Ni square, which is intrinsic impedance. So N represents the electrons, P represents holes, and Ni refers to intrinsic concentration, that is intrinsic carrier concentration. So for an N type, the equation will be with minimum hole, and for P type, so P is equal to Ni square by Nd, where Nd refers to concentration of impurities, and for minimum electron concentration, N is equal to Ni square by Na, where Na refers to concentration of acceptor impurities. So these are the two equations, and we can see that in both the equations, Nd and Na, that is acceptor and Nd value is inversely proportional doping concentration, whereas in Ni, that is intrinsic concentration, is in the numerator, which is directly proportional. So directly proportional to intrinsic is available, but here we have got square, which means option 3 and option 4 is wrong. Looking at the first two options, we have directly proportional to doping concentration, but here it is inversely proportional, so option 2 is our correct answer. Next question, consider statements S1 and S2. S1 is at resonant frequency, impedance of series RLC circuit is equal to 0. And the second statement is in parallel GLC circuit, increasing the value of G results in increasing the Q factor value, which is correct, and the options are provided here. So let us analyze each statement separately first. Looking at the first statement, it is all about series RLC circuit. So in a series RLC circuit, R is equal to R plus J into XL minus XC. At resonance condition, we have to know the value. XL refers to inductive resistance, which is equal to omega L, and Xc refers to capacitive resistance, which is equal to 1 by omega C. So at the resonance condition, the value of XL is equal to Xc. Substituting that in the previous equation, we will get the value of Z is equal to XL minus Xc will be 0. So the remaining value will be just R. So the impedance value will be resistive. But in the statement, it is mentioned that at resonance frequency, the impedance is equal to 0, which is contradictory. So statement 1 is false. Now let us analyze the second statement. So the second statement is about parallel GLC circuit. So under parallel type, the Q factor value is equal to 1 by G into square root of C by L. So we can see that it is inversely proportional to value of G. So whenever G increases, the value of Q decreases since it is inversely proportional. But the statement given is increasing the value of G results in increasing Q factor, which is again contradictory. So the given statement 2 is also false. So both the statements are false, which is corresponding to option 4, which is our correct answer. Next question, a source of angular frequency 1 radians per second has source impedance consisting of 1 ohms resistor in series with 1 Henry inductance. The load that will obtain maximum power transfer is. So to get a maximum power transfer value, the value of load impedance should be equal to source impedance conjugate value. So this is the condition to maintain. And to get maximum power transfer, P max will be equal to Vs square divided by 4 into Rs. Now let us draw the circuit. We have a source here followed by one resistor in series with an inductor, and we have a load over here. So this is the circuit, and the value are given as 1 ohms and 1 Henry inductor value. So this combination makes it as series impedance Zs value. Now let us calculate R plus JXL, which is equal to 1 plus J into omega L. So substituting the values of L and R, we will get the same value. Now the ZTH value will be equivalent to 1 plus J. Substituting the series values and all, we will get the resultant as 1 plus J. The load value will be equal to ZTH conjugate value as per the condition we have seen, which is equal to 1 minus J now. So to get the value of 1 minus J, it is nothing but 1 plus J conjugate value. So this is the value to get the maximum power, which means we have to connect a resistor in series with a capacitor to get the value of 1 minus J. Only then the value of Zs will be equal to R minus J Xc. So the circuit will be now R followed by an inductor, and we have a source here, and in the load side we will have a resistance R followed by series connected capacitor of 1 farad. So this connection will get the value of 1 minus J, will make the maximum power get transferred to the circuit, which means connecting 1 ohms resistor in parallel with 1 farad resistor is our option, which is belonging to option 3, which is our correct answer. Next question. For a PLL phase locked loop with a Gilbert cell mixed based phase detector to maintain lock, the phase error between incoming reference signal and VCO output must be maintained between. So the question is all about phase locked loop. Let us see the basic concept and the parameters involved in that. So PLL, phase locked loop, in the sense it is used to demodulate FM or PM signals. So this is the ultimate work of phase locked loop. The Gilbert cell that we use in this particular phase locked loop, that is Gilbert cell multiplier, is used to get better accuracy when mixing reference and the VCO output. So whenever we mix these two signals, to get a better accuracy, we use this Gilbert cell multiplier within the circuit. So less phase error will be obtained by making use of this particular multiplier. Next is the phase detector, which helps in managing input and error signal by comparing and giving out the error signal, which is E of t, which is equal to k into phi out minus phi in. So the difference between the input and error signals will be detected by the phase detector. And in voltage controlled oscillator VCO, it locks the input signal if the input is within the locking range. So only when the input is available within the lock-in range, the VCO will perform this particular operation. So the range for maintaining is 0, less than pi, less than pi. So this is the range to maintain, and which is also called as the active range, because only then the input will be locked using this VCO. So the question is all about the range which is belonging to option 1 between 0 to pi is our correct answer. Next question, in a prototype filter, the series arm and shunt arm impedance should be. So in general, for a prototype filter, the value of Z1, Z2, where Z1 refers to series impedance and Z2 refers to shunt impedance, is always equal to R0 square, which is equal to a constant K. So this is also called as a constant prototype filter or a defined impedance filter. So to maintain a value of Z1, Z2 is equal to K, Z1 and Z2 should be opposite sign, and it also should be of reactive type. Only then this particular condition for a prototype filter will be matched to get a constant value of K. So Z1, Z2 should be opposite sign and reactive type, which belongs to option 4. Reactive and opposite type is our correct answer. Next question, if the maximum electron density for E layer in ionosphere is 9 into 10 power 6 electrons per centimeter cube, then its critical frequency is. So to solve this question, we need to know the equation, which is critical frequency, which is equal to 9 into square root of N max. So Fc is nothing but the critical frequency, and N max refers to maximum electron per meter cube. In question, we have got in terms of centimeter cube. We have to make sure that we convert that also. So 9 into square root of, the given value is 9 into 10 power 6 centimeter cube. So we will get it as 9 into square root of 9 into 10 power 12. Solving this, we will get 27 megahertz. So this answer belongs to option 3, which is our correct answer.